So no KSP, no solubility equilibria on the exam next week. So we'll material end more or less at the end of the acid-base chemistry topics. So you'll have a little bit of extra time since you won't be working on modules and stuff. Definitely use that time to study the acid-base chemistry. So work on titrations, work on all those different types of stuff. Don't slack off on that. This is meant to help you with getting a handle on that material. And we'll sandwich the KSP stuff, the solubility equilibria stuff in with a kinetics material that comes after this. We'll have a little bit more time for that. The acid-base stuff, I feel like lopping on more stuff is unnecessary. It's hard enough on its own. Hopefully that doesn't knock us out of sync too much with the other section. Okay. So we went over buffers. Practically speaking, buffers, they have this, the application is just that you can prepare something that resists pH change. In terms of calculating pHs and stuff for buffers, it's a little bit easier than some of the other stuff because you can just use this Henderson-Hasselbalch equation as an approximation. Let's take a look now at titrations. Okay, so there are titrations from a problem-solving perspective are very similar to what we've already done. It's just kind of getting a handle on putting everything together that can be difficult. So these are sort of practice over everything that we've done. And then there's a little bit of confusing parts involving like changes in volume, but that's not too hard to get a handle on. So let's start out with strong acid, strong base titration. So in a titration, you have this setup. So the experimental setup for a titration is it helps to have some visual on this to see what's going on. So you have what's called a burette, and the burette will have markings on it. So this is a very standard experiment that you might do in like if you're really lucky enough to go to a high school with a chemistry lab, this is something you might have done in there. So at the bottom you have a stopcock, and then you fill this thing up. So in this case, we're going to do, this thing's full of acid. And so you, down here, you have some base. So this is our base. Oh yeah, sorry, I have to go back and deal with the first exam. I'll try and get that done before our next exam. So you've got a burette and it's full of acid, and you've got base in a beaker. And when you titrate, when you open up the stopcock, so right here, this thing can be opened, and you can push acid So if we take this stopcock and we open it, so we turn it like this way, acid will start pouring into this flask here. And the amount of acid that goes down we can measure that because it's going to disappear from up here. So these little graduations on the side of your red allow us to know how much acid we're adding. So essentially what we're doing is we have adding strong acid from your burette. Well, we can leave out the burette, let's say. Adding strong acid in known quantities to a solution, in this case of strong base. So this is for a strong acid. Strong base titration. And so what we can do is we can see what happens. We can look at what happens along the way as we add in this acid to this base. So we can constantly, so we can monitor. Typically, what you're doing is you're monitoring the pH in this beaker. So you add a little bit of acid. You add a little bit of acid, and you look at the pH change. And then you add a little bit more acid and you look at the pH change. You add a little bit more acid and you look at the pH change. And so there's a lot of different reasons that you might be doing a titration. Right now, we're just kind of looking at it in a fundamental way to just kind of summarize everything that we've done in acid-base chemistry. But these have applications in analytical chemistry and a bunch of different places. Yeah, so let's take a look at a problem then. So let's say we have 50 milliliters of nitric acid. At a concentration of 0.2 molar. Being titrated with 0.1 molar sodium hydroxide. And so we can look at the pH. We're going to look at the pH as we do this titration. So the 50 milliliters, the way that this is going to look, so this is sort of, it's more or less the same as the setup up top, only now inside of our burette we have the base. Oh yeah, sorry about the exam grades. I've just kind of like slipped my mind. It's just a data entry thing. I have to go in and re-enter all the test grades. And I need to do it when I'm like well rested because I'm nervous. I'm gonna map someone's grade wrong. It's silly that the Canvas system doesn't have a way for me to kind of get back into the grading history and just copy those. So now we're doing sort of the opposite here, where we are taking base. We've got 0.1 molar sodium hydroxide in here. And down here we have 0.2 molar nitric acid. And we know how much we have. We have 50 milliliters of that. And we can look at what's going to happen as we add in. So we're going to add in certain amounts of sodium hydroxide. So we can see with the pH. So we can look at a bunch of different points on this in this titration. So we can say what's the pH before any sodium hydroxide is added. We can say what's the pH after 10 mils of sodium hydroxide is added. What's the pH? Now after, say 50 mils of sodium hydroxide is added. Then we get at 100 mils and say what happens to the pH then. That's when things start to get a little bit more interesting. And we just keep adding base in and asking what happens. So this is essentially how all of these titration problems are set up, or at least the ones that are complicated are set up. You're adding increasing amounts of base, and you're just asking what the pH is. So really what you're doing is, if you think about it, is you're just doing a neutralization reaction. So at the beginning, right, it's like I haven't done any kind of neutralization. Yeah, this is strong acid. This would be a strong base, strong acid titration. Yeah, good question. But yeah, so we're increasing at the beginning here, right? We haven't added anything. So it's literally just like, all you're really asking is, what's the pH of this solution? And then as you start to add in more base, what we're doing is we're neutralizing some of that acid. So it just becomes a neutralization problem. Like you're just kind of asking about a neutralization reaction over and over again. So it's like I neutralize a certain amount of the acid with this much base, what's the pH? Then I do another neutralization reaction. So I increase the amount of acid that's being neutralized, what's the pH? And I keep doing that until at some point, right, I'm going to exceed the amount of acid that I have in solution. And now I'm kind of on the other side of the neutralization reaction. I have excess base. And so now I'm calculating the pH based off that. So initially, so you can imagine different points along this. Let's just start by looking at the first part of this problem. So we're saying, what's the pH before any sodium hydroxide is added? Well, for this one, our pH is just going to be equal to the negative log of the hydronium concentration. So all we really need for this part is to look at our concentration of strong acid. So because it's a strong acid, let me move this. So we've got 50 milliliters of 0.2 molar nitric acid inside of this flask. All we're asking here is, what's the pH at that point? And so we know that the pH for a strong acid is just going to be the negative log of the concentration of the strong acid, since that's going to equal concentration of the hydronium in solution. So you'll note that the volume doesn't matter because we're only interested in the concentration here. And so our pH comes out to be 0.7, which is what you would expect for a solution of strong acid. And then we can look at the next step, which is just what happens when we start adding in sodium hydroxide. So now we've sort of started the titration problem. Okay, so now we got to, the only thing that's new here, the only thing that makes this a little bit of a pain is you just have to track the, you have to be careful that you don't mess up the volumes here. So initially we have, in our flask over here, we have 50 milliliters of nitric acid. So now we've added 10 milliliters of sodium hydroxide. Remember, this is a 0.1 molar solution of sodium hydroxide. And so now we have 60 milliliters there. But before we deal with any of the volume, the proper thing to do, I think, is to look at the neutralization reaction that we have here, not HCl. So I have nitric acid in the flask, and I'm adding in my titrant, which is sodium hydroxide. So I'm titrating a beaker full of this acid with my base over here. And so I know that my reaction is going to produce just water and sodium nitrate. But we want to, when you're doing stoichiometry, I think the easiest thing to do, or the smartest thing to do, is just back things out into moles for this. So you'll note that everything here is in terms of concentration and volume units. What you want to do is start out figuring out the number of moles of acid that we have up here, because reactions take place in terms of moles. This is generally what we work in. So to calculate the number of moles of nitric acid that we have, remember we just take the concentration of nitric acid, which is 0.2 molar. So I'm just getting that from up here, 0.2 molar. And I want to multiply that times the volume that we have there. It's 50 milliliters, but because this is in liters down here, remember I want to do a conversion there. So I'm going to say 0.5 liters. Or 0.05 liters. And so what I end up with is, leave some space here. What I end up with here is 0.01 moles of nitric acid. So that's what I'm starting out with. That's my initial concentration of this. And then I can think about how much sodium hydroxide I just got rid of any assignments due this week. So take the time to work on the practice stuff. I thought the titration homework was still in there. I can go check that after class. I just moved it right before lecture started, as I was thinking about kind of where I wanted you guys to be at the end of the week. But yeah, so we've got 0.01 moles of nitric acid here. And then we want to figure out how many moles of sodium hydroxide we have there. So we've added some amount of sodium hydroxide in. And we can calculate that. So we're going to back that out into moles as well. So you can look at how much of your acid is reacted here. So we start out with 0.01 moles. How much are we going to end up with? At the end of the reaction, we're going to have 0.009 moles of that, and we're going to have 0 moles of sodium hydroxide. So this is at the start, this is the finish. That's just based on the stoichiometry. And then when we want to calculate our pH, then we just take this new value that we've calculated here. That's sort of what the, so this is our new value of moles of acid that we have. So we have 0.009 moles. But this is the thing you have to keep track of, is that we've added 10 milliliters to our initial 50 milliliters. So our volume has changed. So you just need to be careful of that. So this is our hydronium concentration now. So remember, because we're dealing with a strong acid, the hydronium concentration is equal to whatever the concentration of the strong acid is. So this piece here is just remembering that you're adding volume. So you're always adding, in a titration, you're always dealing with a liquid that you're adding into a liquid, which is not how we always ask the questions when we're dealing with neutralization, but it's always true for titrations. So you're always adding in, if you go back and look at your experimental setup, every time I add in base here, right, I'm changing the volume of what's inside this beaker. And since I'm changing the volume of what's inside this beaker, no matter what problem I'm asking here, I have to account for that volume-wise. I have to account for that in my concentration. So not only am the pH changing because I'm neutralizing some of my acid here, which is sort of the obvious thing, that if I take some base and I add it to the acid, that's going to change the pH, but I'm also changing the volume, and that will also change the pH. And so you'll note that I plug in my new volume here. So I'm diluting my H+ concentration. It's a much smaller change, but yeah, if there was, so one question here is that if this, because I'm doing this stuff in my head here. So most of the time for the acid-base stuff, we're dealing with a 1-to-1 stoichiometry. But if you were dealing with like 1-to-2 or 1-to-3 or something like that, where the question is if it had to be balanced and it wasn't 1-to-1 anymore, yeah, you would have to consider that in your stoichiometry question, your stoichiometry calculation here. So if this was 1-to-2 or something, that changes things. Okay, so this process that we just did here, you can just keep doing this over and over again. So if we add a little bit of acid, it's all right. So we've seen our pH change here. We started at a pH of 0.7. We add some base. We actually do the transform here. Let's see what our new pH is now. So it's the negative log. So now our pH goes up a little bit, and this is it. This is what we would expect. This is the result we would expect here, which is that our pH is just going to increase as we add in more base, because we're making the solution less acidic. Okay, so then we can go on and we can say, well, what's the pH? If I add more base. So for the strong acid, strong base, these strong acid, strong base problems, the calculations aren't super intense. They're kind of repetitive in some sense. Okay, so we're looking at this from the perspective of, like initially we added 10 milliliters. Now we're saying, since the way that the experiment's being done is you're sort of watching this thing incrementally go down. We talk about it from the perspective of how much total has been added. So it's not like, I guess what I'm saying is, here we're saying what's the pH after 10 milliliters of sodium hydroxide has been added. Now we're saying what's the pH after 50 milliliters of sodium hydroxide is being added. That means that 50 milliliters incorporates the 10 milliliters. So it's not 10 milliliters and then an additional 50 milliliters. It's 50 milliliters total. So the 50 milliliters sort of includes the 10 milliliters. Yeah, it's like if you were trying to talk about the passage of time or something, and you were like 10 minutes passed, now 20 minutes have passed. The 20 minutes isn't added to the 10 minutes, right? You're just saying, okay, no, it's additional. We're just sort of at a different point in the timeline. And that's the same thing here. We're looking at this in terms of 10 milliliters and then 50 milliliters. So your total volume change here is just whatever this number is. It's not like you're adding more and more. You could phrase the question that way, but it's not typically the way things are phrased. Okay, so again, we just do the same exact calculation now, though. So we say we've got nitric acid and sodium hydroxide. We don't really care what the products are, but we will eventually when we get to weak acids. And we know how much nitric acid we started with was 0.01 moles. So now we need to figure out how much sodium hydroxide is included in 50 milliliters. And we come out with 0.005 moles. So at the beginning of this reaction, we have 0.005 moles. At the end of the reaction, we have, because we're still below the amount of, we still haven't consumed all of our acid. At the end of this, we'll have this. And now we've consumed half of our acid. So we have 0.005 moles. So start, this is the end or the finish of our reaction. And now we just want to calculate our pH. So we say, well, what's our nitric acid concentration? That's going to be equal to the amount of acid that's left over here, 0.05 moles or 0.005 moles, divided by our total volume. And so if we go back, again, we started out with 50 milliliters here. Now we've added 50 milliliters. So we have 100 milliliters. Of course, we want to be in liters, so I multiply that times 10 to the negative 3. And I end up with 0.05 molar in nitric acid, which is equal to my proton concentration, and that allows me to calculate my pH. I'll answer that question in 1 second. So somebody asked the question, so now we see that our pH has increased again to 1.3 from 0.82. So that's our expected result, is that the pH is going to get progressively higher. So the question is, wait, why wouldn't you use 0.009 moles of the acid? So we're looking at this, so it depends on how you look at the reaction or how the question is asked. But typically, I think for titrations, or at least one way that you can ask questions for titrations is, it just depends on how the question is phrased. So we're phrasing the question as, if we read it here, it says like, what's the pH after 10 milliliters of sodium hydroxide is added? What's the pH after 50 milliliters of sodium hydroxide is added? So we're not asking we're not asking it sequentially, like what's the pH after 10 milliliters, and then what's the pH after an additional 50 milliliters? It's an additional 50 milliliters to the 10. We're just saying what's the pH after 50 milliliters of sodium hydroxide is added. So it's similar. I was trying to draw the I'm saying it's not like the sequential addition. You're asking in terms of like a continuous timeline or a continuous line of volume here. So you're watching this volume change as you go down, and it's similar to the thinking if you're thinking in terms of time, like if you're thinking in terms of time for the class passing or something, you can say like, how bored are you after 10 minutes of class has passed? How bored are you after 50 minutes of class has passed? You're not saying, when you say how bored are you after 50 minutes, the assumption is that that includes the original 10 minutes, right? So you're sort of encapsulating the initial amount of volume that's passed in the same way that you would with the time inside of the second question. Yeah, okay, cool. Yeah, so down here, I'm just being, yeah, so we're here. So something that I'm doing quickly is we're in milliliters here, but we're trying to calculate this in terms of molarity. And so I'm just multiplying times 10 to the minus 3, or here as well. I'm multiplying times 10 to the minus 3, because that immediately converts milliliters to liters. So I'm doing that in my head. So if you're in milliliters and you want to go to liters, just multiply times 10 to the minus 3. It's just a fast way to do it. If you want to write out the whole thing, you can do that too. Okay, so I think in this next step, things get a little bit more interesting. So you can see what we're doing here. So all we're doing is we're doing a neutralization. If you step back for a second, we do a neutralization, and then we have to consider the volume change. That's sort of a new piece. But then we just calculate the pH after the neutralization reaction. So these are problems that you've worked on before, hopefully. It's just now we're kind of putting it all together. I was hoping to at least get started on the weak acid stuff today. Maybe we'll still have time. All right, what's the pH after 100 milliliters of added? Again, we're starting out with 0.01 moles of nitric acid. And now we're saying, what if we added 100 mils instead of 10 or 50? And so we need to calculate out how many moles of sodium hydroxide we've added. And we come out with 0.01 moles. I'm going to do it on my calculator just to be sure, just because it's early. I don't do as much math as I used to. Yeah. So we've added 0.01 moles. Okay, so this is sort of interesting. So at the beginning of the reaction, this is what we have. But now you can see that we've completely neutralized our acid. We have 0 of this and 0 of this at the end of the reaction. So what's going to be our pH here? So I take a strong acid and I neutralize it with a strong base. Yeah, just 7. Good. So our pH here is just going to be set by whatever the solvent is, which is almost always water in this class. And so it's just 7. So I don't even have to consider like anything to do with the volume changes. Let's take a look at what happens after that point. So this point here is special. So the equivalence point. When the concentration, or say the number of moles. Moles of base added is equal to the moles of acid. So it's just the point in your titration. So in this particular case, because we're dealing with strong base, strong acid, it's the point in the titration where the amount of base that you've added is exactly equal to the amount of acid that you've added in the flask. So it's just a stoichiometric, when they're stoichiometrically equivalent, that's your equivalent point. And so for here, because we start out with 0.01 moles of acid, the equivalence point is when we've added in exactly 0.01 moles of sodium hydroxide.
Dr. Dragna, quick question. Yep. I understand the math and why it's equal to 7, but it seems intuitively, you added 50 and it only went to 1.3, and then suddenly you add just another 50, 100 total, and it's suddenly neutral. It's gradual. Is that because it's exponential pH? As far as you move up the pH scale, or I mean, it just suddenly jumped.
Yeah, I don't think it's the. Yeah, let's say, so the question is, why is it that the pH, you can see that and this is something that we can see when we make a plot of this. You can see that like we have 10 milliliters, we add another 10 milliliters, things change a little bit like you would expect, 0.7 to 0.82 as I add a little bit more base. If I add 50 milliliters, I see it go up to 1.3. When I add 100 milliliters, it doesn't go up linearly. It goes all the way up to a pH of 7. And this is because at the beginning of the reaction, so as we approach the equivalence point, the pH will start to change rapidly, which doesn't answer your question. It just kind of restates what you're asking about. And that's because in the beginning, if you think about the beginning of this reaction, at the beginning of the reaction, you have 0.01 moles of nitric acid. So if I add a little bit of, I guess I'm trying to think of how to phrase it. So at the beginning, you have a lot of acid. And towards the end, as you start to approach the equivalence point, you have much less acid. So like if you're thinking in terms of like the change in the concentration of acid, it's going to be much more significant as you start to approach the equivalence point. So going from, like if we go back to here, for example, if we go from 0.01, now we've gone from 0.01 to 0.005. And so your concentration has changed from 0.01 to 0.005. In this here, when you start to approach the equivalence point though, this thing is rapidly starting to approach 0, I guess. So like as you get closer to the equivalence point, the amount of acid in solution approaches 0 rapidly, whereas at the beginning, it doesn't change as much. I don't think I'm doing a great job of explaining that.
Well, pH is an exponential function. You go from 1 to 2, and that's a 10 factor, correct?
That's true, but we're staying in the logarithmic scale, so like as I'm saying,
we don't I agree with what you're sidetracked. I'm sorry.
Yeah, no, I agree with what you're saying. It is exponential, but we're staying in the pH, like we're staying in pH, so we're staying in the exponential sort of domain or whatever. So it should be linear. Like that doesn't, you are changing by an order of magnitude, but because you're not, but because you're plotting it as a function of log, that shouldn't matter. Just like if you're following the pandemic, for example, and you take the exponential change and look at it, just plot it as like a function of, now I'm getting really off topic, but if you look at like number of cases, let's see, how do we plot that usually? It's like time, a function of number of cases versus time, is that right? Or time is a function of number of cases. But if you look at a plot of, if you look at a plot of number of cases, a function of time for the pandemic, you'll see that it's an exponential curve. So it'll look something like, what exponential looks something like this. But if you take and you do the transform on it where you're doing log on that, you actually use the exponential transform, now it starts to look like this. So if I take, God, my math is really atrophied, but number of cases, if we take the log of that, so now we're taking log of number of cases, it makes it linear, right? So it's like the logarithm, I guess what I'm trying to say is the logarithm accounts for the fact that it's exponential. So that's not why, that's not explanatory as far as why it's changing so rapidly as you approach the equivalence point, at least in my mind. Okay, anyway, all right, let me get back. So yeah, so the reason it changes rapidly as you approach the equivalence point is more because of you don't have any acid left at that point. So you have a small number and you're subtracting out. So like the relative change in the concentration of acid, I guess what I should have said, the relative change in the concentration of acid near the equivalence point is much larger than when you start out. I think that's the reason why it changes. I think that's the right explanation of why it changes really rapidly. So. If the relative concentration of acid is much smaller, near the equivalence point. So I guess if you think about it in terms of, like if you're thinking about it in terms of like bank account, like if you're starting out the month with, I don't know if it's exactly true. Let me think. I'm not sure if this is an exact analogy, but if you're starting out the month with $100 and take away $1, that's not a significant change in the amount of money you have. You start out with $100, now you've got $99. But if it's towards the end of the month and now you've only got like $2 left in your bank account and I take away $1, now, that's a 50% change. So that's why as you start to approach the equivalence point, you start to see the pH vary rapidly. It's because this relative amount is the way it's changing is the relative amount is, the relative change is much larger. All right, we got 2 minutes left. Let me finish this. Let me do one last little bit here. So beyond the equivalence point, so at least we can start on the weak acid stuff. So if we had 200 milliliters of sodium hydroxide, again, we just start out with the neutralization reaction. But the amount of base that we've added here is going to be 0.02 moles. So at the end of this, now we're going to have 0 moles of nitric acid, but we're going to have an excess of base. So when we want to calculate our pH, we want to calculate it from this concentration of base that we have here. So we have 0.01 moles of sodium hydroxide, and we've added 200 mils to the initial 50 mils, so we have 250 milliliters of solution there. So this is equal to our sodium hydroxide concentration, which of course is equal to hydroxide. And so what you want to get though is you want to get proton concentration. So there's a couple of ways to do that, but one way is to take this relationship here. So now you've just calculated the hydroxide concentration, so you need to back it out into proton concentration. And as you'd expect, your proton concentration is very small. And so if we take the negative log of that, we end up with a pH of 12.6. So now we see that after the equivalence point, our pH is going to be dominated by the base that's in solution. So you're always going to have an excess of base. So if you plot this, so if you take pH and you plot it as a function of volume of sodium hydroxide added, you end up seeing the curve that looks like this. And so right here is our equivalence point for a strong base being titrated into a strong acid. And so, yeah, in this case, this would be 100 milliliters. And this is where the moles of sodium hydroxide equals the moles of HNO3. So this plot, this titration curve or whatever, describes sort of this entire process. At the beginning, we have a lot of acid, and then we start to add base, we see the pH sort of gradually rise. As we approach the equivalence point, it starts to dramatically change. And then once we get past the equivalence point, we have excess base in solution. And so now we just see that we have basic pH, and that starts to kind of level off as we get out farther away from the equivalence point. Yeah, you could also find POH and subtract from 14. That's probably that's another way to do it. But so this is strong acid or strong base. When you titrate them together, you get something like this. And the weak acid, weak base titrations. So what you do is you take like a weak base and you can titrate it with a strong acid. Or if you want to do something that's corollary to this, you could take a weak acid and titrate it with a strong base. And it's the same kind of idea. You just do a neutralization, and then you have a pH problem afterwards that you're working with. But because you're having to deal with equilibrium in those cases, the calculations are a little bit lengthier. And so we'll deal with that we'll address that on Friday. Yeah. All right. Let me take a break, and then I'll be back for office hours in a few minutes. Okay, let's see. Yeah, I went and grabbed the stack exchange thing for the titration curve equivalence point question, and that made me feel a little bit better. It's the explanation on there is like super complicated, but it's just that function blows up as you approach the equivalence point. There's probably a intuitive way to explain it that I'm not getting at particularly well. Let's see.
Dr. Dragna, I have a quick question regarding like the problem that we just went over.
Go ahead.
So like when we were calculating the pH after 10 milliliters of NHO added, we like when we made the conversion, we multiplied the moles by 0.05 liters. And I'm just confused of why we wouldn't like multiply it by 10 times 10 to the negative 3.
Um, 10 times 10 to the negative 3. Oh, like for the 10 milliliters?
Uh-huh.
So the which part of this are you asking about? So here we're just calculating the number of moles of nitric acid that we started with. And so that the number of moles that we started with is just the number that's originally in the flask here. And the number at the 10 milliliters here, that's the moles of sodium hydroxide that you've added. So what we're trying to do is we're trying to get rid of these volume pieces here and just talk in terms of moles. So, you know, if we forget about the fact that we need a solvent to do chemistry, you could say, how many moles of nitric acid do I have here and how many moles of sodium hydroxide have I added? That's all I'm doing here. Does that make sense?
Yeah, I just like wrote it down wrong, I think.
Oh, okay.
So looking at it confused me.
The volume, honestly, the volume stuff, like I remember when I was taking general chemistry, although it's been a very long time, that stuff always confused me. And I think it's just, I think it's just a familiarity with like working in a lab or something. It's hard to, at least for me, like I remember just having trouble like imagining what, it's just hard for my brain it was hard for my brain to kind of track what the hell is going on and all these different things. I don't really have a good way of getting used to that. I think drawing pictures helps me.
So we only had to find like the initial concentration of the acid because that's what we were adding the base to. So if like the question was reversed, you were adding an acid to the base, you would only have to find the initial for the base since you're adding acid.
Right. Yeah, right. Yeah, the important things that you're worried about are the number of moles of whatever you're starting with. Here it's acid, but it could be base. Number of moles you're starting with here, and then how many moles of whatever you're adding in you have. And then the concentration of the volume comes back into play at the very end of the question. Does that make sense?
Yeah, thank you so much for clarifying that.
Mm-hmm. Okay. We go for acid-base practice.
So I'm still a little confused on how, like, on some parts you added the millimeters and like on other ones you didn't. Could you like go over a little bit more over like on the ones that we were doing during the class, but on the third one that like we added like the 10 millimeters on the second one, but on the third one we kept it to like 50 millimeters.
Here?
Yes. And
So
then like on that one.
Yep, go ahead.
So, because you know, like on the number 4, we didn't add anything like for the millimeters. We just kept it to the 100 instead of being 150. Because like I noticed that on the number 5, we added the 100 millimeters, but like
Here.
Yeah.
Yeah. So the only reason that we didn't have to worry about the volume here is because we're at the equivalence point with a strong acid, strong base. So no matter what volume you have, you're just taking the pH of pure water. Does that make sense?
Yes.
So this is just the pH of pure. sorry, go
What
ahead.
about the third one? Yeah, because like on the third one, we actually didn't add it like the, because we were supposed to have after the 50 millimeters, but we didn't add it.
Here?
Yes.
Yeah, so here we start out, we do our calculation, we calculate the number of moles of acid and base and stuff that we have. We calculate our final moles of acid. And then at this point, I take the nitric acid concentration and I say, okay, well, I've got this amount of acid left over. I did add back in the 50 milliliters.
Oh,
So we
yeah, I
start
see
out with
that.
50
Sorry,
milliliters.
yeah.
Yeah.
And then you add the 50. Okay.
Yeah, maybe I should be a little more explicit. I keep doing it in my head just to kind of move things along, but maybe I'll be more explicit about that in class on Friday, since that seems to be confusing. But ultimately, all of that stuff is like, you don't have to worry about the volume at all until the very last part. So generally, all you have to think about is the number of moles of acid and base that are reacting. And then at the very end of whatever they're at, whatever part of the titration you're in, you consider the volume that you have there. Like so here, after we do our neutralization reaction, we say, well, we've got this excess base here. So then we have to consider our total volume. So the total volume only affects the final pH. So like when you're actually going in and calculating the pH, you have to know the concentration, which involves a volume term. So you have to divide everything by the total volume. But before that, you're trying to just work in moles exclusively. Okay, let's see. So we've got acid-base problems, part 1. I think somebody in class is asking about that too. I don't know if we'll get to polyprotic acids for exam 2. I'll have to look and see what we did in the LEs. Let's see where we get. If you can do the weak acid, weak base type, if you can do weak acid, strong base and stuff like that, then the polyprotic's a small step forward. Question 1 from practice problem set 2. And question part 1, problem 1, acid-base problems. Let me see if I can. Christine, are you talking about, yeah, part 1, okay. So complete neutralization reaction performed by combining 200 mils of lithium hydroxide and then nitrous acid.
Yes. What throws me off is that they end up in the same moles, so it becomes zeros, like the lithium hydroxide and then the nitric acid. What throws me off is I don't know what to like do after. Like, how do you find the pH of the like resulting solution? Because
Sure.
like what you're left with is the salt. So I guess that part throws me off.
Yeah, I can see. I understand your question. So this is a good one. I feel like this is at least titration adjacent in terms of questions. So the problem is a complete neutralization reaction is performed by combining 200 milliliters of 0.20 molar lithium hydroxide and 100 milliliters 0.4 molar nitrous acid. And then the question is, what is the pOH? And so really, if you think about it, this is essentially the same as a titration question. It's as if you're taking, like if you were doing, let's say you had nitric acid in a little beaker. If I've got 200 mils of HNO2, and then I'm, in a sense, titrating in 200 milliliters of 0.2 molar lithium hydroxide. So the only difference is I'm not calling it a titration. I'm not setting it up in like an incremental thing or anything, but it's essentially the same idea. But yeah, so if we look at this, 200 milliliters of did I mess up my volumes here? 100 milliliters of, yeah. But yeah, so I've got 100 milliliters of nitric acid at 0.4 molar and 200 milliliters of 0.2 molar lithium hydroxide. So if I write out my neutralization reaction here, important point, not nitric, nitrous. So first step is write out the neutralization reaction. And we end up with lithium nitrite and water. We start out by calculating the number of moles of each thing we have there. So if we want to know how much lithium hydroxide we have, that's just going to be 0.2 moles per liter. And then the amount of nitric acid that we have is going to be 0.4 moles per liter multiplied times the volume that I'm just converting into liters in my head. And then you end up with the same number of moles for each of these. They sort of hint at the fact that they should be the same moles because it says complete neutralization, which is implying that the reaction is done stoichiometrically. So you end up with 0.04 moles of this and 0.04 moles of this. So at the start of this reaction, and at the end, we've got 0 of this, 0 of this, and 0.04 moles of this. And so the question that is being asked is, what's the pH or POH of this final solution? And the confusion point is, so, I guess the initial instinct is, well, I've got no acid or base left over, so maybe my pH is equal to 7. That's not correct. The thing you have to recognize here is that this is a weak acid. Which means that the conjugate base for this lithium nitrite is going to be a weak base. Does that make sense? Because that part of this rationale is sort of the key, I think, to this.
I think I got it flipped, but yeah, I got it now. Thank you.
Okay. Yeah, so once you recognize that the salt is a basic salt, then you just want to set up an equilibrium here. So you'll notice I'm dropping the lithium off because it doesn't really matter. It's a spectator ion. But now your problem is, after you're done with the neutralization reaction, now your problem is just this weak base problem. It's like saying, what's the pOH of a solution of lithium nitrite? And so we need to figure out what our concentration of lithium nitrite is eventually. We might as well do that now. So we have 0.04 moles of it. And so now we have to go in and make sure that we have all our volumes correct. So we had 200 mils here and we mixed it with 100 mils. So our actual concentration of lithium nitrite is 0.04 divided by 300 times 10 to the minus third. So that's our lithium nitrite concentration. Yeah, so then we just want to go in and we want to work this like a normal rice kind of problem. It's okay. Our initial concentration of nitrite is 0.13. Obviously, we don't care about water. The change is going to be X. We're going to gain X of this. We're going to gain X of that. And so at equilibrium, we're going to have this. So what they don't give you in this problem that you need to solve this is your K value. So you need to know the Kb or Ka of nitric acid. So okay, thanks. Yeah, so in an exam situation, we would give you this, like on this exam or whatever problem, we probably pulled it. I think I pulled this from an old exam. I'm sure we gave you the Kb on the front page. So if you're at least recognize that you need the Kb and that's not given you in the problem, that's pretty good, I think. That shows that you kind of understand kind of how the problem needs to be solved, I think. But so then we can write out an equilibrium expression for this. That's just Kb is equal to HNO2 times hydroxide divided by NO2 minus. And we can plug in our values. So it's X squared divided by 0.13 minus X, which is equal to 2.5 times 10 to the minus 11th. 2 times 10 to the minus 11th, this is a very small Kb. So this is much, much less than 1. And so we can assume X is very small. Because what this is telling us is it's saying, what remember K describes how far the reaction is going to go to the right. And X is literally like, X is a measure of that in a sense. It's saying how much of the reactant is going to be converted over into product. And so these two things are related, X and Kb. So if Kb is a really small number, we can assume that X is going to be a really small number. And so we can do this nice simplification here where we just say that it's X squared over 0.13 is equal to 2.5 times 10 to the minus 11th. And so X is going to be equal to the square root of 2.5 times 10 to the minus 11th times 0.13. That can't be right.
Just out of curiosity, is there any reason we couldn't just like use the OH equals square root of Kb times Cb to begin with? Like why we work it out this way?
Like one of the equations that they give you in the, I generally stay away from those equations just because they naturally fall out of this. Like that's kind of what we were doing.
Yeah, I was confused on, so like I saw the answer key and like I was trying to understand what the explanation was trying to say, and I didn't get what they meant by approximation formula, and I was like looking it up and everything, and I was like, I don't get it.
Yeah.
That's why I asked about it, because I wanted to get the conceptual part of how you got there.
Yeah. So those approximations that they use, I guess I don't teach those. I guess some of the other instructors do. I don't like those just because they're not as general. So if anything changes, like the stoichiometry or something changes, or you're maybe, I think even if you're starting out with like some starting amount of either of these things or something, then those approximations don't really work. So it's okay to use them, I guess, if you know when and when you can't apply them. then there's no problem in using it. But there are situations in which you are trying to figure out like what the hydroxide concentration is, where that equation will not give you the right answer. So I guess what I'm saying is, and it's hard because I am doing an approximation here, but generally speaking, if you go through this process and you understand what you're doing, you'll always get the correct answer. If you're using the approximation, that's fine, but you need to know when you can and cannot use it. And that still requires you understand this process. So it's kind of a moot thing to try and use the approximation as a shortcut. Yeah, I guess even kind of knowing what I'm doing, I still don't use that equation. I always go through the KB thing because this doesn't feel like a lot of this, for me at least, this isn't super laborious. Yeah, I think in general, this shouldn't be super laborious. So that approximation just doesn't save that much time. And I think it just, if you're, I guess if you're like, I have no idea what I'm doing, you need to take a guess, the approximation's good. But what you really want to be able to do is understand what's happening here and be able to translate that into this equilibrium expression to solve it. That's like a very generalizable way of thinking about equilibria. Does that answer your question?
Yeah.
I guess my general advice is like, don't mess with the approximation thing unless you really know what you're doing, which most people don't because, we're in an introductory chemistry class. So I would just stick with the KB and using the equilibrium expressions.
So when you have a strong, sorry.
I know you've like explained it a lot in class, how you use like the 1. So do you always like approximate x to 1 in the denominator? Like when is there a case that you can't do that?
Oh, like when like you're talking about like right here, like how do I know to get rid of x?
Mm-hmm.
Yeah, so it's hard. I know there's so much stuff to keep track of. So you don't really know when you cannot approximate x. It's sort of indicated by this number. So if this number is really small, generally this number is going to be really small.
Oh, okay. So you compare it to like whatever the KB is or K.
Yeah, and that gives you an idea of whether or not the approximation will be valid. And that's because those two numbers are related. Like x is going to be really small if KB is really small. If it fails though, like so if this number, for example, here we calculate a number, it's 1.8 times 10 to the minus 6. I can come back and compare that to this number up here. So really the approximation that you're testing is you're saying 0.13 minus x is approximately 0.13. And you could say like, you could set a limit on that. You could say, well, within like 5%. So if it's 0.129 or something, that's close enough for us, If I look at if I take whatever I come out with over here, so this is equal to x. If I take that out and subtract it out, what does that equal? Well, scientific notation all starts to look the same after a while, but it's 0.0000, 1, 2, 3, 1, 2, 3, 4, 5, 1, 8. No. Trying to get rid of my little scribble scratch there to keep track of the zeros. But yeah, like what does this number equal? I don't know, 0.13 minus 0.000018. That equals 0.129999982. Right, so our approximation, we can say, is probably pretty good because x is very small. In this number, news app. Thank you, iPad. This number, for all practical purposes, right? If your calculator spit this out, you would just call it 0.13. Does that make sense?
Yeah, it makes sense,
So
especially.
Yeah, it's kind of counterintuitive because like you're solving for x, like you're approximating and then you're taking whatever your approximation was and then like testing it against the original number. So like you're kind of, I don't know, to me it always felt a little bit uncomfortable because you're kind of sort of saying that this number is valid in some way, valid enough to compare it, but it turns out that that's fine. What were you saying before I cut you off?
Just like what you compare it to like whatever the KB and KA is. So when is it like not, so I guess like if it was like 10 to like what, like the -2, that's not like, you couldn't use the approximation, or would it still?
Yeah, so it's, you really, you kind of have to just, I mean, there are probably like ways to test it. You really want to like try the approximation and then compare it. So like, so like here it works out if I were to change things up, let's say in like my OH minus concentration was equal to 0.1. So I guess you can't make a strict thing where it's like, well, if KB is small, then the approximation always holds, because it's not just KB that matters, it's also what your starting concentration is. So for example, if our starting concentration was not 0.13, but was something like, I don't know, 1 × 10⁻⁶, now this number starts to be comparatively large. Does that make sense? So it's dependent not only on this, but also on this. So when you're doing it, so that to answer your question in like a practical way, what you do is you make the assumption. So if you have no idea, you don't have to think about any of this. You can just say, I don't know if this assumption is going to be valid. You go in and you subtract out X, and then you get a number for X, and you come back over here and you see if this holds. Is 0.13 minus X, you can ask yourself the question like, is this true? So you would say, well, you come down and test it, see what number you get, and say, is whatever my approximation, like, is it within 5% of whatever that starting value was? Like, I guess it's like, is another way to say it is X less than 5% of the starting concentration? So here our starting concentration was 0.13. So for like here it's 0.13. And so X was equal to 1.8 × 10⁻⁶. So if I wanted to see if it was less than 5%, I could just take and divide those two numbers and multiply times 100. And I see that indeed it is significantly less than 5%. Does that kind of make sense?
Yeah, I think that clears it up like a lot.
Yeah. So you make the assumption and then you test the assumption. And if the assumption doesn't hold, then you have to go through and actually use the quadratic formula. When I took general chemistry, that's how I was tested on it. And you know, I had to work out by hand on the exam with the quadratic formula what some of the answers were, which was fine. Generally when we get these types of questions in class, I think we for the most part have avoided the quadratic just because it takes a lot of time. You guys have access, because you're taking it online, you have access to, like a quadratic solver or something. So you could conceivably just take and always never making any assumptions and go and plug it into the quadratic solver and be fine. So that's also an approach, right? So the quadratic equation always works, but the approximation sometimes fails.
Regarding this, if this question was like a weak acid, weak base, can that ever go into complete neutralization? Would there always have to be a strong base or acid along with it?
You can write out a weak acid, weak base neutralization reaction. God, I guess I'll say we don't give you that on an exam. So we'll always give you a strong acid, strong base.
Or a strong acid base with the weak acid or base.
Right, exactly.
Okay.
Yeah, it'll never be weak acid and a weak base. You can do that, obviously, like there's a way to model that. But it just gets more complicated for obvious reasons. I think kind of what you're intuitively kind of figuring out is that you have to take into account both salts that form, which gets messy.
So whenever we have a weak base, we always do that second equilibrium problem where we take the salt that forms and then like divide it out into its ions and then solve for the OH or H concentration?
That's right. Yeah,
Okay.
that is exactly right. So if you have a neutralization reaction, so what Taylor said is a very good insight, which is just that if you have a neutralization reaction that you're working through, and one of the components is a weak acid or a weak base, in this case it's a weak acid, you're always going to end up with some sort of salt over here that you have to then go back and figure out the pH from. So you have this second step with equilibria, if it's a complete neutralization.
Can you go over question 1 on the second practice?
Yeah, the exam will just be acid-base stuff, so we'll skip the solubility stuff until next exam and lump it in with kinetics. Oh, good. Yeah. So here's the titration problem. So if you can work, if this problem, problem 1 from the part 1 makes sense to you, the titration stuff, if it's not making sense to you, you're not super far off from getting that. They're like super similar. I think the problem with the acid-base stuff is there's just so many different situations that can come up, but the titrations do a good job of kind of wrapping up all of those situations into one problem. All right, so this one is, what is the pH at the point during a titration when 30 milliliters of 0.2 molar HCl has been added to 31 milliliters. It's a weird volume of stuff to start out with, whatever, of 0.05 molar ammonia. And then it tells you that HCl is a strong acid, which you should know. And then that the Kb is equal to 1.8 times 10 to the minus 5th for ammonia. All right. So what is the pH at the point during titration? So this problem, if you use the word titration, but it really is just the same as the last problem that we worked. It's like I'm taking 31 milliliters, at least the setup for it is similar. I have 31 milliliters of base. And then I'm adding in this case from a burette, that's really the only difference, 30 milliliters of 0.2 molar HCl. And then it's just asking me what the final pH is. So what's the pH? So you start out just the same way that we did the last one. You say, okay, I've got a neutralization problem. In this problem, I don't know that you're at, I don't think you're at the equivalence point, which is what, would be essentially complete neutralization. So we start out, step 1 would be kind of calculating the number of moles of each thing there. So moles of HCl in moles of ammonia. And we just do that by multiplying times the volumes. So when you're looking at the neutralization reaction, you always want to be in moles. So neutralization reactions, you think in terms of moles. So that's why we're going into moles here. And so I just come up here and I look at this then. Say, okay, if I start out with 0.006 of this, and I've got 0.0016 of this, at the end of the reaction, because it's a 1-to-1, I'm going to have some acid left over, but I'm going to have 0 of this left over. So at the beginning, this is the start, and then this is the finish. Okay, and then, so this one's sort of interesting. Sorry, it's just so messy, it's not even useful. This is a good follow-up to the last problem that you guys asked about. So at the end of this, you would also have some of this ammonium chloride salt formed. So what is our pH of this solution? Well, we have to consider all the different things that kind of contribute to the pH. So what's present in the solution before equilibrium? So let's say at the end of the neutralization reaction, we can kind of think about like, what do we have in solution? So we have H plus, we have 0.004 moles of that. We don't have any ammonia. We also have Cl minus. We'll put this in the So you also have Cl minus there. Right, but that doesn't actually affect the pH at all because it's not even a weak base, it's a spectator ion. So we need to consider, these are things that have an effect on the pH. But we can make our lives easy by recognizing that if you have a strong acid, which is what HCl is, the contributions of the weak base, the contributions to the pH of like a weak acid, this NH4, is going to be probably totally negligible. So I can say my H plus concentration is going to be approximately equal to whatever my HCl concentration is. And so you just need to be sure here that we're using the right volume. And so we start out with 31 of one and 30 of another. So you have 0.03044 moles, and that's going to be over, we're going to take both of these volumes and add them together until that'll be over 61 times 10 to the minus 3 liters. 0.072 molar. And so our pH is going to be equal to the negative log of 0.072. Which is equal to 1.14. So, you know, there's this other thing that's in solution that does contribute to the pH. Let's see. When I calculate the NH4 plus concentration, that's going to be equal to 0.0016 divided by 61 times 10 to the minus 3. You can calculate what the contribution to the pH is from that if you wanted to. But we know that they give us Kb to be jerks. So we know that Ka is going to be equal to Kw over Kb. Which is 5.5 times 10 to the minus 10th. So we know that this is going to be a very small contributor to begin with. So if we look at, if this is the weak acid that we're considering, and we compare it here, we know that not very much of this is sort of getting back to this approximation thinking, that whatever amount of 8 plus forms from that, which will essentially be X, is going to be small. This number is going to be probably very small. And we can assume that it's going to be, we know it's going to be much smaller than 0.026. And if we come back and look at our acid concentration over here, oops, it's 0.072 molar. So we know that it's probably not going to contribute much to the pH, generally speaking. So I know that's confusing. So weak acid salt in the presence of strong acid will typically contribute a negligible amount to the pH. So if I end up in a situation in a neutralization reaction where I do my neutralization reaction, so like for example here, I've got a strong acid and a weak base, and we can think about the different scenarios that you can end up with. But if I end up in a scenario where I have excess hydrochloric acid, excess strong acid, then that's all that's going to matter for the pH. Yes, I have some weak acid that forms, but that weak acid just contributes very little to the final pH. Just because it's a weak acid. It's sort of like the strong acid just kind of dominates. So you're adding in like a tiny amount of H plus from the weak acid, but it ends up not mattering for our calculation. And so you can do this simplification where you just take the negative log of the strong acid concentration. Does that make sense? Maybe?
And this is what happens when the reaction does not go to completion.
This is, so we can think about, let's look like, we've got strong acid and a weak base. So the reaction is going to completion. The neutralization reaction is going to completion. I'm saying that the equilibrium part down here for the salt that we have to consider doesn't matter. So,
but in the last problem, it specifically said that this is a complete neutralization. This one did not specify.
Oh, I see what you're saying. Yeah. So I just, going to completion. Yeah. So you're not. Yeah, the last problem it said complete neutralization, which is different from going to completion. I can see how that's confusing, but yeah, it's in the last problem. It's when you're adding. I would describe it as stoichiometric amounts. When you're adding equivalent amounts of acid and base. It's like when this number and this number are equal, that's complete neutralization, or where you're at the equivalence point, or you've added stoichiometric amounts of acid or base or whatever. So when those are exactly equal to 0, then we have to come over and worry about this. Okay, now your question, now what you're saying makes good sense. Then you have to worry about this. If I'm after that, so if this number ends up being greater than this, then I don't have to worry about this. If I'm less, like if I have less HCl, so all of this is consumed, then again, I have to worry about the amount of innards that I have over here. So basically, you always have to worry about when you're titrating, like if you take a strong acid and you mix it with a weak base, you always have to worry about the weak acid that you form. Except for the case where you add so much HCl that now you're past what is essentially the equivalence point. And now you don't have to, you can ignore this and just use the HCl concentration. This is why the titration problems are really good for kind of learning all of this stuff, because it sort of encompasses all of that. So in a titration, you can think about it. If I was adding in, if I start out with some amount of ammonia and I'm continuously adding in HCl, I'll sort of encompass all those cases. I'll see the neutralization before I hit the equivalence point. So before I, do complete neutralization. So I'll have no HCl left over and excess ammonia in some of the salt formed. And then I'll hit the equivalence point where I'm at the complete neutralization, where I have 0 of this and 0 of this. So this really matters a lot. And then I'll go past that where I have excess of HCl. And so I sort of see all of those different pieces as I go through my titration curve.
If this is a neutralization reaction, then why wasn't there water one of the products?
Yeah, you don't always form water in a neutralization reaction. So, and this is one of those cases. So if hydroxide is one of the bases, then you'll form water. But if your base is not hydroxide, then you don't necessarily form water. And that's what we end up seeing here. Generally, I'm trying to think of other cases where this is. So generally, if your base has a nitrogen in it, or it's one of these amine, or I don't know how they describe it in the homework exactly, but if it's got a nitrogen in it, those are the ones that won't form water. There are probably more cases than that, but I think for us, that's generally what we see. I think I'm trying to think of like the most generalizable thing that you can say about it. I think in general, you will almost always form a salt, but you don't necessarily have to form water.
So when the acid and base moles do not have the same number of moles, when calculating the pH of the titration, you just have to worry about like either the acid or the base reactants. You don't have to worry about the products.
I'm sorry, say that one more time.
It's not a complete neutralization. When calculating the pH, you only have to use like the the acid or base that's in the product. I mean, the reactant and the reactant.
Right. Well, I don't know. So if you're before the complete neutralization, you might have to worry about both. So like in the situation where you had like let's say you had like 0.001 moles of acid that you react. So your start is let's say you're starting out here. At the end of this reaction, you'll have 0 of this, but you'll have 0.0006 of this and 0.001 of this that forms. So now you have to, now when you write this out, I guess what you're saying is still true. You have to do the base, like you worry about the base, but you still have to account for the acid in the product. So you would start out with.
And the product is negligible, right?
Well, I don't know. I don't think so in this case.
Oh.
So you just want to write them both when you're writing out the equilibrium there. So here, at this point, you have a buffer, really. So I guess, yeah, I guess I could work through the, so here you could probably use the pH is equal to the pKa plus the log. So yeah, before the equivalence point, after you've added a little bit of acid, you have a buffer. Let's look at this. So let's say you're doing, let's just look at this exact problem. And then I gotta go. Pencil die. Never had this happen. Oh, there we go. Okay. Let's just say arbitrarily, let's say I have, it's like hard to represent everything that's going on in the reaction, but like, let's say we start out, let's forget about concentration for a second. Start out with 0.1 moles of ammonia. If HCl is less than 0.1 moles, but greater than 0, so you have to have added some HCl. Then you use the Henderson, it's like easier to write out the damn equation than these guys' names, but Hasselbalch equation. If HCl moles equals NH3 moles, then you use weak acid salt. To calculate the pH. And then the other scenario that you can have is HCl is greater than 0.1 moles. Then you use the HCl concentration to calculate the pH. So there's really only 3 places you can be. You can be at a place where, let's say you're in like 100 mils of water, just to make it an actual, so you go to concentrations you can work at, so you can be in a place where you've added HCl, but you haven't gotten to the point where you've completely neutralized all of the NH3 that you have there. So in that case, you'll end up with, it's like, let's say that you added in 0.05 moles of this. So in that case, at the end of the reaction, you'll have 0 of this, but you'll have some amount of ammonia and you'll have formed some amount of its conjugate acid. And so you have a base with its conjugate acid. And so in that case, you have a buffer, right? That's our definition of buffer, is that we have a conjugate acid base pair there. So here you're in like a buffer. And then as you sort of move through this, now when the number of moles of HCl is equal, so if this is now 0.1, when those 2 things are equal, now you just have a situation where you have some of this salt left over. And so you use that to calculate the pH, but you don't have any ammonia there anymore, right? So 0 this, but I have some of this. So I use that to calculate the pH. And then as I move past that to where I have too much of this, so like 0.2 moles of HCl, now I have 0 of this. Yes, I form some of this, but I have a strong acid there, and so I just end up using that to calculate the pH. So those are really the 3 scenarios that you find yourself in for most of acid-base chemistry. So in titrations as well, you can either be before the equivalence point or after the equivalence point or at the equivalence point. Each one has its own separate sort of mathematical treatment to calculate the pH. Does that make sense?
Yes.
Yeah, I know it. I know it's confusing. Like like it's not exactly clear when to use what treatment, but this is sort of a, and there's some intermediate cases here where things can get super confusing, but this is a general problem solving like workflow to use for these types of problems. So, all right, I am gonna go. What am I going to do? I need to go remake those problem solving videos for unit 2. So I'll probably do that right now. But I will see you guys on Friday, and good luck studying. You guys are doing the right thing by working out lots of problems. So keep up with that. Okay. Bye, everybody.